So let us talk about equipotentials. Equipotentials are very important in the study of electrostatics and physics at large. So what are equipotentials? Well, instead of just telling you, I'll show you. Let's suppose we have a charge of plus Q placed here. We know that this charge is going to create an electric field around itself. In that sense, so there we go, the charge creates an electric field in that sense around itself. So at any point around the charge, we can calculate the electric field. But also, we can calculate the electric potential anywhere in space surrounding this charge. So let us draw a concentric circle to this charge. Let's suppose I draw this circle here. Okay. So I suppose this circle is of a given radius, and all points on this circle are the same distance from Q. So we know that from electric potential of a point charge, which is given by Q over 4 pi epsilon r, is that fine? 4 pi epsilon r. So this is the expression for electric potential of a point charge. So from this expression, we can say that all points on this circle are actually having the same potential, since they have the same distance from the point charge itself. And so what does electric potential actually mean? Electric potential is work done. That's what we mean by electric potential: work done to move a unit charge, or to move a charge of plus 1 coulomb from infinity, okay, from infinity to a point in the electric field of a given charge. So what if we move our charge and we bring it and place it somewhere here? Let's say that's our test charge Q0. What if we now begin moving the test charge along the line, along this arc of this circle that is surrounding the point charge? Are we really doing any work? Let's see what that is. Is there any potential difference between a point A and another point B here? There is no work, because all points at this circle, at the arc of this circle, are actually at the same potential. So you cannot do any work by moving from A to B, since there is no difference in the potential. Let me show you another good illustration of this. Suppose this is a building. So this is the ground level, okay? This is the ground level and this is the building. Suppose I move a big mass and I place it here. This is a big mass. I place it at this point. It has a potential energy given by the mass times the acceleration, gravitational acceleration, times the height from the ground. That's the potential energy that this object has. What if I move the object up to here? Is there any change in potential energy? There isn't any change, because potential energy only depends on the height. As long as I'm on the same altitude, I will not be doing any work. Okay? In geography, we use lines called contours. Contours to represent lines on a map with the same altitude, and at those lines you actually don't do any work in moving an object. So that's very important to us as physicists. Now, just like we have contours on maps, we also have equipotentials in electric fields. There are points at which are at the same potential, so you don't have to do any work in moving a charge from one point to the other. So that's very important. Equipotentials are points with the same potential, or points around the charge. Points around the charge with the same potential. So the potential at A, the potential at B, if I add another point here, perhaps C, they will all be at the same potential. So there is no work done in moving a charge around this. Now, equipotentials can be of different sorts. We could have equipotential lines, for example. This concentric circle here can be considered an equipotential line. Yes, it is an equipotential line because all points on it have the same potential. If I draw another line, okay, perhaps of a smaller radius, oops, I don't want to use that same color. So, okay, here we go. If I draw another circle here, this is also an equipotential line. If I draw another line, that's also an equipotential line. So the surface that is bound by this equipotential line is what we call an equipotential surface. So we can have equipotential points, equipotential lines, and equipotential surfaces, and you'll hear the word equipotential surfaces being used more often. Those are surfaces in electrostatics, surfaces at which you don't do any work in moving a charge around it because the potential is the same. So surfaces that are bound by equipotential lines are called equipotential surfaces. Okay. Also, you can see that the electric fields are always perpendicular to the equipotentials. That's one property of the equipotentials, and that's what makes the work done to be zero. So that's very important. So why is it that the equipotential lines are always perpendicular to the electric field lines everywhere? Well, we already discussed that dV, the electric potential, is given by E dx. Now, to be more specific, electric potential is a scalar quantity, but the electric field and the direction, the electric field and the equipotential lines are actually vectors. So, to be more specific, I should write this as dV equals vector E dot vector dx, where vector dx is the direction of the electric field or the equipotential line at any chosen point. So, to be more specific, this is going to be E times, okay, times dx times cos of the angle between E and dx. So that's going to be dV. Now for the electric potential to be 0, or the work done to be 0, so for dV equals to 0, then we'll have E dx cos theta equals to 0, and E and dx will actually be equal to 0, but cos theta, E and dx may not necessarily be 0, but cos theta here will have to be 0. So this means that theta would have to be 90 degrees strictly. So that's why the electric field lines and the equipotentials are actually perpendicular at all points. That's a good point to observe when drawing equipotential lines. And